Okay, so we will begin today's lecture, and today's lecture is titled Pure Bending of Beams. What do you mean by this? That means a beam that is subjected to along the length of its longitudinal axis, which is subjected to pure bending. Now when is this possible? If you have a beam, this is the longitudinal section of the beam, it can have a cross section. I will tell you about the cross section. So if this is the longitudinal section of the beam, and let us say the cross section is rectangular. So this is the cross section. There is a width B and there is a depth H and length is L. Now how to subject this beam to pure bending? One simple way is that let us again take it is as if it is simply supported. That means one end hinge, end A hinge, end B on a roller, so that there are only 3 reactions, because we don't want more than 3 reactions, because otherwise the problem becomes indeterminate, statically indeterminate, that we do not want. So this is the geometry of the beam and the support condition. Now how it is going to be loaded? We want this to be subjected to pure bending. Okay, so pure bending means we have seen that other day we derived that rate of change of moment dm by dx is plus or minus, it was equal to V, shear force at the cross section. So the rate of change of moment, that means if there is any change in the moment along the length of the beam, then you will get a shear force. Now we don't want a shear force. We are not going to apply, let us say we can avoid any axial force by not applying an axial load to the member. So how to get this? I think best thing is to ensure that there is no change in the bending moment. So best one is, let us say that this is subjected to a moment m here and a moment m here. At the two ends I am applying moment. So along the length, now the depth need not be shown. Beam is so we idealize this as if it is a line which is the centroidal line, and we have we also show roller like this, so that it is having a free motion in x direction, and this is our z direction upwards positive, y is going into the plane of the paper, and then this is subjected to pure bending moment. So we have at this end a moment m, at this end a moment m. Now free body diagram. There is no other load. There is no other load. So this is AX, this is AZ, this is BZ. So we get from equilibrium axial force all forces in x direction, sum of all forces. So you get AX equal to 0. Now as such there is no load on there is a moment here m, and there is a moment here M is applied. So now what about AZ plus BZ? That is also equal to 0 because there is no other load on there is no external load on as such on the beam. Now let us take moment about point A. So we get BZ into L, BZ into L, which is anti-clockwise. Yes, and then there is external moment. So you have a clockwise moment here. So if you call this as this moment as anti-clockwise about this point is anti-clockwise negative. So you have a clockwise moment here plus M, and then you have another moment here which is anti-clockwise minus M. So moment about A, sum of moment of all forces about A equal to 0. So therefore we get here that BZ is equal to 0. So no BZ equal to 0. Since BZ equal to 0, from equation 2 here you also have AZ equal to 0. So that means it is simply, so at any cross section, so if I cut it here, so this is 0, this is 0, and this is also 0. Yes, still you are having load on the member, no support reactions. Now let us take a section at a distance x from the left end, draw the free body diagram. It is like this, there is no support reactions, but then there is a moment here M. Here at any cross section you have a shear force X at a distance x, positive as per our positive convention, and plus you are having a moment at section x. So we get here, since there is no vertical load, so Vx is no shear force, and Mx, you take moment about this point, you get moment of V equal to 0. This M is clockwise and there is anti-clockwise moment over here. So this is Mx equal to M. So that means at any cross section x you are having a moment. So that means throughout along the beam, this beam is subjected to pure moment. So this is beam is subjected to pure moment. So that means there is a pure. So we are talking of such beams. When we are saying pure bending of beams, we are talking of this. There is no change of moment along the length of the. What are the other situations when we can have this? Yes, not supposing we have a beam when this is possible, again simply supported. I am talking of a situation when we can, and it is subjected to, let us say, at 1/3 point of the beam you have two loads of equal magnitude. So all these, not that everything has to be equal, I am taking for simplicity, this is L by 3, L by 3, L by 3. So free body diagram. Free body diagram is very important in engineering. We can't get anything without drawing free body diagram. So please never have, please call these points. So this is at yes, at A. So this is a hinge. So you have AX in X direction, AZ in Z direction. Here you have B, Z in. So these are the reactions. So this is in equilibrium under the action of 2 external forces and 3 reactions. So we get, if you sum all the forces in X direction, we get AX equal to 0. If you sum all forces in vertical direction, so we get AZ plus BZ equal to 0, no, equal to 2P, yes, but these are the opposite direction. How to get? Let us take moment about point A and A. If you take moment of all forces, so we get here this length is span is L total. So BZ into L anti-clockwise, then P will produce a moment, so it will be clockwise. So P distance is 2L by 3. Again this P minus P, again this also will produce a moment that is clockwise. So P and the distance is from A is L by 3. There is no other force, so this is must be equal to 0, and therefore we get BZ equal to two by 3P plus 1 by 3P. That makes it, yes, that makes it P. So we get BZ equal to, right. And then from equation 2, AZ plus is 2, therefore AZ also will be equal to P. So we have a situation that means this beam, there are 2 loads, A and P. The reaction, of course it has to be balanced, so that is how you have the 2 reactions also are P and P. That is all, and it is in a state of equilibrium. Now let us try to see how is the bending moment diagram. How do we draw bending moment? Below this diagram, let us sketch the bending moment diagram. You know what is a positive? A positive bending moment as per our sign convention is that if this is the beam element of length dx, a small element, a positive moment produces tension at the top, compression at bottom. Okay. But then here the situation is just the reverse. Here this P, if I take a section just before this P over here, so P into L by 3, PL by 3 will produce, P into L by 3 will produce a bending moment PL by 3, but then the tension is at the bottom. So that means it is a negative bending moment. So this will be like this, negative. Let me draw on the lower side. Similarly here also the same, it will be symmetrical. And then at any distance it will P into X, it varies linearly. It varies linearly. After this P, what is the value? P into if x is this, so it will be equal to how much? I think it will be equal to, you take x now, let us take x here. So it is P into x positive, and then this will produce, negative. So it is P into x and then this P into x minus L by 3, because this is L by 3. So minus P into x is producing a tension at the bottom. So this is minus, and then this P is producing tension at the top. So this P into, so plus this P into x minus L by 3. X minus L by 3, and that is all. So that is the bending moment at this section. So that is equal to bending moment M. But what is the value? Value is this px, so that is M is equal to P into L by 3, PL by 3, but with a negative sign. Yes, so that means here this horizontal line from here to here, it will remain constant. So what I want to say, that by if you having two loads, then this is the portion where there is no change of bending moment. So this is the section, this central L by 3 is subjected to pure bending moment. So this is pure PM. While this one is, of course, this is changing, so there is also be shear force here, and of course shear force is there, but in this portion there is no shear force. But this P and this P will nullify, and shear force diagram here is, if you draw shear force diagram on the top of this, so you get here. So this, there is a shear force down, so that is a negative shear force. This is upward, so here it has to be down. So that is on a positive phase, it is a negative. So there will be a constant shear force P. And the moment we cross this P, it will P minus P, so it will become 0. So here this portion, it is 0, and again here shear force, it is positive shear force, because if you come here, so you will get a negative P, and here it will be upward, so this will be positive P. So this is our shear force diagram, SFD, and this is BMD, SFD, BMD. So in the portion where there is a pure bending moment, no change in bending moment, see, you have a 0 shear force. So this is 0 SF. It has to be, because otherwise dm by dx equal to V. Okay, so we can always have some sections which are subjected to pure bending moment. Now next I will talk something about the cross section of the beam that we ought to take. So this is, I have already given you that, yes, I have taken a cross section. We are taking this pure bending. The cross section, of course, this can be rectangular, and we are applying load in the plane of the symmetry, so that there is no twist. So this is the plane of the symmetry, vertical plane of symmetry. So it divides this cross section into two halves. So we are talking of bending of those beams, and these beams are having cross sections which are having vertical plane of symmetry. So a triangle is okay. This again is having plane of symmetry. A circular cross section is okay because this is also having a plane of symmetry, and loads are all applied in the plane of symmetry so that there is no twist. We are not. Then we can also have a section which is let us say we call a box section. Yes, this also has a plane of symmetry. It's possible. We can have a channel, but the channel has to be such that, so it has to be used like this, then this has a plane of symmetry, but not otherwise. If you turn it by 90 degrees, then that cross section will not have. So loads have to be applied in this plane. So all such cross sections are possible. You can have a T section. We have an I section. I think many of you must have seen these girders, these steel girders which are of this. So this is called web. Web is this portion, and this top which are flange, they are, so this is called flange. So it can have equal flange, it can also have unequal flange, like a rail line. Rail line normally has a section like this, our railway line. Yes, that is also symmetrical about this axis. So it is all possible, but not this. If you use this C section like this, so we are not talking of this. And we can use a T section. This is called T. This is called an I beam. I section. This is called a T because it looks like T. This also has a vertical plane of symmetry. This doesn't have a plane of symmetry. It has a plane of symmetry, but about horizontal axis, so I cannot apply load in that plane. So all these are possible. So we are talking of bending of beams which have a vertical plane up. So I will draw a dumbbell shaped cross section. So we are talking of any cross section which has this is the vertical plane of symmetry. So the loads are applied in the vertical plane of symmetry. This is the loading plane. This must be kept in mind. If you don't apply here, if you apply a load here, then this cross section will twist, which we do not want. We want to apply these loads over here. So it is a beam. Of course, the other criteria, so one is the cross sections. What kind of cross section that we are? So it's a pure bending moment. Cross section has to be like this. These are the, and then cross section has to be like this. And then what about, is there any relationship between the length and the depth of the beam? Normally we will call, see, what is important in the bending of the beam is the length and the depth. B is not now important, because B, we are applying load in the plane of the symmetry, so B can be very small. In fact, we are assuming, technically we are assuming that B is it's a very, very thin in y direction. The beam is very, very thin. So B dimension is not important. That means y dimension it is very small dimension. Loads are in Z direction. And what about, is there any relationship between L versus H? Yes. This is called, if you have a depth like this and length like this and depth like this and length like this, is there any difference? Yes, there is. We'll call this beam, this is only H, this is H, this is H, this is L, this is L. We'll call this beam, you see, there is a ratio H by L or L by H. Here L by H is very large compared to L by H here, or H by L here is very small compared to what H by L here. So this beam we'll call it slender beam, and this one we'll call it thick beam, not slender, thick beam. So what is the criteria, geometrical criteria? What is the geometrical criterion? I will have this parameter H by L. So if H by L is small compared to unity, then it is slender. So we are going to consider in this discussion today slender beams. So we are going to slender beams, not thick beams. Because there are certain considerations that have to be kept in mind when we are considering thick beam or beams which are not slender. Some mechanistic behavior has to be taken into account, and while here now during discussion I will try to. So for slender beams, for beams having vertical cross section, which is symmetrical about, which has a plane of symmetry, a beam which has a vertical plane of symmetry. Theory was developed some more than about 200 years ago, around beginning of the this is now 21st century, 20th century, beginning of 19th century, that means 1800, beginning of 1800. 28 September. So what was the geometrical, what will you call is small, slender? I will just give you some idea about. See, H by L, L by H, less than, what will you call less than? 1 by 20, 1 by 50, yes, okay, 1 by 100, all right. They can be treated as slender. but if it is 1 by 5, 1 by 10, I think I will be a little concerned, because I will not be able to call that beam as slender. So we are talking of these ratios. So for such a beam, theory was developed, technical theory was developed, and of course technical theory means it will have some approximation. Technical, so technical theory of beam, technical theory of beam. It is not exact, because this will not be taking or considering all types of beams. It will consider only slender beam, it will consider only beams which are having vertical plane of symmetry. So two names are important, and one name is Bernoulli. So as a student you must know Bernoulli. And now there are a number of Bernoullis, I think they must be from the same family, Noulli, Bernoulli and Euler. I think the theory or the formulation or the development of the formulae, etc., is started with Bernoulli, and final touches were given by Euler. In exactly, I don't remember now, some 1800, maybe 30 around. So you can see that our mechanics has about 200, it's 200 years old, about 200 years old, yes. So whatever we are learning is not of something which was done yesterday, but it has a long history. So these two gentlemen, these two scientists, mathematicians, mechanicians, we also call them, people who deal with or who work in the area of mechanics, they are also called mechanicians, not mechanics, mechanicians. Mechanician, like scientist, and so you have mechanicians. So these person, mathematician, so people who, mathematician, scientist, engineers, of course. Engineers, people don't call them as scientists. So engineer, so but now we have engineer scientists, engineers who do a little bit of thinking and come out with certain results, certain analysis. They are called scientist engineer. Anyway, so these are the various terms, mechanician. So we are talking now of Bernoulli-Euler theory. Bernoulli-Euler beam theory, because it was developed by them, and till today it goes by their name. You must not forget people who gave you the basic analysis. Technical theory of beam or Bernoulli-Euler beam theory. Of course, this is for slender beam theory, so this is for slender. Now there are certain assumptions on which whatever now we will be deriving is based on. What are the assumptions? I think you must have by now realized. I will exceed today's lecture by a few minutes, so please be patient. So this is Euler-Bernoulli beam theory. So assumption in Euler-Bernoulli beam theory is the following. What is the assumptions? First one is very important, that the beam is slender. Unless it is slender, whatever we are going to do, so that means h by L is small compared to unity. So everything will be okay, slender. 2, if it is slender, in that case what they said, that originally the beam is, I am just drawing a small section, a small longitudinal section of the beam. So originally the beam is like this, and when the pure bending moment is applied, it gets deformed, it assumes a shape, pure bending moment, so it will assume a shape like this. Then this center line will get, and so this is subjected to, you have pure moment. What they said, that if you have a point here P, originally this vertical line, this is called transverse normal, vertical normal. You draw a line perpendicular to x axis originally. Now what will be the shape of this normal? So P comes here, P, and this normal will assume a shape like this after the load or bending moment is applied. Originally what is there? This angle is 90. Between x and z axis the angle is 90. So transverse normal, this transverse normal. So this is a normal if you are taking a longitudinal section. If you take B, also B means width of the beam into consideration, so we can also call it transverse plane. Transverse plane. So originally this normal, this trace is normal. Now what they said, that even after bending, if it is a slender beam, this angle will be remaining 90 degrees. What is the meaning of this? If this is remaining 90 degree under pure bending moment, yes, what is the meaning of this? Meaning is that there is no change in the right angle between x and, so a normal section here, an element we had taken here, that element is still all the angles are still normal, 90 degrees. So that means what? How did it define earlier? Shear strain. So shear strain in the plane x and z. X is this, z is this, xz plane. After loads are applied, after bending moment is applied, it is still normal. There is no change in the right angle between x and z. So this is equal to 0. This is not an assumption. In fact, we can prove from the exact theory that this is true. But then I would like to explain this. Under pure bending moment, we are saying that yes, this will be, to start with, and that this all the normals will maintain their normality with respect to x-axis throughout the process of deformation. So, this xz, this is called shear angle, transverse shear strain. This is called transverse shear strain. Strain is also called by many authors as shear deformation. So, this transverse shear deformation is 0, there is no shear strain. So, second assumption that we will say that yes, this angle will always remain 90 throughout the process of deformation. Now, the third assumption that I will like to highlight. So, this must be kept in mind. We can prove through an exact theory that this is, although I am saying it is an assumption, this is not an assumption when there are pure bending moments acting. It will become an assumption when there is other, this cross section is also subjected to moment and shear force, because then it will become approximate. So, but anyway, to start with, let us say this is equal to this assumption. Third one, we said, on which this theory is based, the thickness or depth of the beam, thickness of the beam what happens to the thickness, this depth, total depth of the beam when it is subjected to pure moment? Will it become less, more, or it will not change? Now, if the beam is slender, there has to be some change. But then if your beam is slender, then what these people assume, these two gentlemen, Bernoulli and Euler, that let us say it does not, thickness of the beam does not change, does not change. They said that let us assume during deformation, during. Third assumption, very important. These assumptions are, now thickness doesn't change. This is the thickness, this is the top fiber, this is the bottom fiber, this is the thickness, and this is your beam longitudinal section. So, this is H. This remains same at all time during deformation. What does it mean? That if you take 2 points in this direction and later on, and you measure the distance between these 2 points, and later on after the moments are applied and then you measure the distance, you will find that there is no change. There could be some change, but we are making this assumption because anyway the depth is very small, h is very small compared to length, it is a slender beam. So, we can make this assumption, and this is a reasonable assumption. So, this means there is no change in these 2 points, no extension or compression. That means the strain in the normal direction is 0. Now, there is one more assumption and then it will complete the whole story, and that is normally done again. Thickness is, and that is what is that fourth assumption which we are going to enunciate. Fourth assumption. Basically, we are talking of a problem because if you don't consider, if the B is very small and loads are all applied in xz plane and xz plane happens to be the plane of the symmetry. Xz plane is plane of symmetry. In that case, we are talking of plane stress problem. Plane stress, because all the loads are in the plane xz. Plane stress problem. But plane stress problem is a 2D. We want to develop a beam theory that is 1D. That means wherein the depth doesn't come in the picture. We want to express everything as a function of x. So in order to simplify the Hooke's law, which will become clearer later, we also make an assumption that the normal stress in, that means normal stress is sigma z in the thickness direction. Normal stress sigma z, which is also written as in many texts as tau zz, sigma z or tau zz, is small compared to other stresses in the beam, because we will be neglecting this. So this is small, that means this is a small quantity. This is a very, very, or I will say it is small, it is small compared to other stresses developed in the beam, in the slender beam, in the slender, again it is slender. What are the, by the way, what are the other stresses? Other stresses is, yes, there will be, the longitudinal fibers will get extension if you apply a bending moment or compression at the bottom, so there will be sigma x. There will be, there can be sigma z, but then we are saying this is small compared to sigma x. Then there will also be, if you take a small element, so on the element you will have a shear stress tau xz. So basically on a beam element, so I am just taking a small element, I am taking, now that means around a point P I am drawing, this is in z direction, this is in x direction. So what are the quantities, what are the stress at point P? It is a plane stress, so you have sigma x, sigma x, sigma z, sigma z. Then on this face you have tau xz. On this face you will have the complementary shear stress tau zx. On this face, this is the negative face, you will have the shear stress which is tau xz, and similarly on this face you have the complementary shear stress, that is tau zx. So in general you have these three, sigma x, sigma z and tau xz. This is at any point in the beam, because we are not considering the width of the beam. So we are not considering stresses perpendicular to the longitudinal plane of the beam. All loads are applied only in xz plane. In that case, this is the only thing. So we are saying that this sigma z is very, very small compared to sigma x, tau xz, etc. There is some reason, because as we will proceed with the derivation, I will show you that yes, by making this assumption we simplify the Hooke's law, and that is needed. So please remember that these are the basic assumptions which are used in the derivation of the beam theory, beam formulae, and these are very important. These are extremely important, and we have to have these concepts very clear before we can embark on developing the mathematical derivations. So these are the four. This is in addition to that the which we make use of that the linear elastic theory means the Hooke's law is there is a stress versus strain is a linear law. Then the displacements are small displacement theory. So these are the standard in all the analysis. So we are not, I am not repeating those. So we are talking of linear analysis, wherein both geometrical means displacements are small and constitutive relation is linear. In addition to that, these four assumptions are necessary. Now I will just tell you the last concept that we will be needing. Now we have so I will take a small section of the beam. It is a small section of length dx. This is the original. So this is your x-axis, this is your z-axis. When it is subjected to pure bending, when it is subjected to pure bending moment, then obviously its shape and size changes and it becomes something like this. So this is moment, and here you must note then there will be, because there are some longitudinal fibers, we call this a longitudinal fiber in the length direction. These fibers which are there, some are getting elongated. See, originally this is the length. Now here you will find these will be in tension, that means this will get elongation. And these are getting, the fibers which are below certain line, they are getting compressed, they are getting shortened. Compression. In between there will be one longitudinal line which will neither undergo any elongation or compression. What will be that line? We call that line or that axis as the neutral axis. Neutral. So you have in the longitudinal direction one. So your x-axis we always coincide with the neutral axis. So x-axis is coincident with your neutral axis. I will always, whenever I will draw, you please take it that yes, my x-axis is coincident with the neutral axis. So this is your x. So x-axis, and once it gets compressed, so can we not find out strains, longitudinal strain? That is very simple. Let us say this small length dx, that means this neutral axis, it will have the dx length, but then forms a, so let us take a fiber, one fiber, longitudinal fiber, call this as R from the neutral axis to the center of curvature. This radius is R. Take a fiber at a distance Z from the neutral axis. So this one is, supposing I want to find out how much is the elongation If I know the elongation, then per unit elongation is my longitudinal strain. I am talking of positive strain, so positive will always be change, which is extension. So I have taken it on that side, on the top side. I am not taking bottom. Although z can change its sign. So this is your x-axis, and z-axis is. So z is perpendicular. Z is this direction. So this is any point at a distance z. So what is the length of this arc length? Let us say originally this was dx. So it will be next. I think I will be using just the last page, 22. 9. So if this is P and Q, call this as P dash Q dash. So what is the longitudinal strain? So I will call it change in the longitudinal in x direction is P dash Q dash is the final, is the elongated length, minus the original length. Let us say this is the neutral axis PQ, so minus PQ divided by the original length PQ. This will give us the longitudinal strain. So what is P dash Q dash? P dash Q dash is equal to R plus Z into the angle. Call this angle is theta. R into theta, yes, R plus Z into angle. So R plus Z into, call this d theta, not theta. Theta doesn't look, d theta into d theta. This is a small length of the beams multiplied by d theta minus PQ will be R into d theta divided by R into d theta. So this comes out to be R will be, so it will be Z by R. So we have got one simple relation, a geometrical relation which gives us a measure of longitudinal strain Z by R, distance from the neutral axis of any point P, and then so the strain, longitudinal strain over there is Z by, of course, if you can know R, what is the radius which this small element has formed into. So then we can have this okay. So Z into R, and now we have now got a simple formula and of longitudinal strain. Now tomorrow I will also tell you how to get the value of R when it is and then we will try to relate this strain to stress. That will be in tomorrow's lecture. So we will stop today's lecture at this point, and so thank you very much for your patient hearing.